is that darker brown stuff. It's actually the bulk of the argillic horizon is below the cemented zone.
So probably what we would describe here is we have sort of an old cultivated AP horizon down to about this depth, because this grass strip has.
Everybody listen up, Marty's explaining the profile here, those that want to listen.
Mr. Microphone.
Microphone, yep.
Mr. Microphone.
They plow deep here, and actually the texture of that plow layer is usually like fine sandy loam.
Okay, so here's what we have. We have a plow zone that comes down to 25 to 30 centimeters. Because this hasn't been actually cultivated in a while, we probably have a thin A horizon that's developing in the upper part of what was that plow zone. Then we have the remnants of this eluvial zone. It's probably something like, we might call it a BE or an EB horizon. These are all pretty sandy. Usually they're like loamy fine sand textures.
Yeah.
And then we're transitioning into this argillic horizon, which probably extends down to about a meter or so, more or less.
Yeah, a little over a meter, as I recall.
Yeah, and then maybe 110. And then, so this is the zone of maximum clay accumulation. These textures in here are probably sandy clay loams.
Yeah, that's
and good alluvial, clay films, argillans and such on ped faces, as well as in some of these silicified fossils. Then below that, down to about 140 centimeters, we have a zone that's still got a lot of iron oxides present. We would probably, it's becoming more sandy, it's transitioning out of the argillic horizon. We would probably call it a BC horizon. We begin to see not only some iron oxides, but some jarosite within the BC horizon. And then below that, from about 150 centimeters or so down, it's much greener and grayer. Much fewer iron oxides are present. Some of us might still want to call this a BC horizon or a CB horizon.
In fact, I like to call it BC, and the true C isn't until you get 8 meters down.
So the textures in the lower bottom of this profile probably are, again, approaching loamy sand type textures, loamy fine sands.
Fine sandy loam.
Fine sandy loams, loamy fine sands. But they contain quite a bit of glauconite, and in fact, if you're doing field textures, the longer you texture it, the more clayey they will feel. Because you're actually converting some of these sandy glauconite pellets into clay-sized material that adds to the plasticity.
It's a tricky thing to texture.
But what's evident is that in this zone, and down for quite some depth, we find jarosite present. And as you poke around in here, digging there, with some very nice jarosite models that are present in this, and sometimes they'll extend all the way down until we hit the unoxidized zone, which at this location is probably 6 to 8 meters below the surface.
At least, actually, I think.
Based on Validera's map, Dell, based on Validera's map right here,
is that right?
that's his his modeled depth.
Oh, okay.
If you go over to that end of the farm, it gets quite deeper, and where we're going to look out near the entrance, it's only about 3 meters.
Marty, do you think that cemented zone, what Dell is calling the cemented zone, represents an erosional surface, and you've got some other materials that are on top of it? It looks like a stone line or something like that to me.
I don't think so.
I don't.
No, I think these are probably formed in place at the time. There's no indication that you've sort of had rounding, transport of any of these materials.
No, but even that, it was just eroded down to there, and then you had some deposition.
No, well, anyway, it works out quite well that the amount of clay that you get down deeper seems to match up pretty well with the glauconite pellets that broke down up above.
If you remove this cemented zone, this is a pretty common looking soil. Looks almost exactly like this throughout the region here.
Right.
Yeah. So,
yeah, this cemented zone, it's just found in certain places. But we are going to see some more of this silicon cementation at the next stop. But there it's actually in a place where it's an active acid-sulfate soil because of land disturbance.
Is there much organic matter in the soil?
No, not very much. In this plow zone, typically we might get 1% carbon, and down into the argillic horizons here, a few tenths. It's quite low. Probably a little bit higher here where this A horizon's been forming.
So it formed the oxidate or the weathering of the soil formed in a forest or something?
Yeah, this is the sediments are very old. The sediments are 30 to 60 million years old. So the landscapes are much younger, but it's very difficult to assess the age of these erosional landscapes. You know, if you're in depositional landscapes, it's a lot easier to estimate the ages. But if pushed, I would say these erosional landscapes are probably hundreds of thousands of years old. We have some erosional landscapes we think in southern Maryland that maybe are 1 million years old, but that's about as old as the landscapes are. And so it's because they're continually, you know, being eroded and cut down. So it's hard to know what an age means. But you know, these are very well developed argillic horizons. We find sort of minimal argillic horizons in, you know, young deposits that are 5 to 10,000 years old. So, you know, this, we know it's much older than that.
Anyway, the glauconite, just a comment on glauconite. That glauconite is a mineral. Some of the stuff in soil taxonomy may sound like it's a sand, and it can be in sand-sized pellets. But when the sand-sized pellets break down, it's still the mineral glauconite. And mineral glauconite is very well defined as a potassium-bearing 2-to-1 silicate mineral, actually a mica. But it's unusual in that it has a large amount of iron in the oxidized in the octahedral sheet of the 2-to-1 layer. And actually it is both ferrous and ferric iron there. And one of the things that we've actually studied, and this is with moss power spectroscopy, is the ratio of the ferrous to the ferric in the oxidized zone versus the unoxidized zone. And it definitely is higher amounts of ferrous iron, but it's not all ferrous in the unoxidized zone. And this also affects the color, and very much the kind of thing that Stuckey was showing, Daryl, with the nontronite. And actually, if you take the potassium out of the inner layer of the glauconite, it's nontronite in my opinion. But anyway, out of that, you can actually see the color change. In the unoxidized zone in thin section, it's a beautiful green.
Sort of a dark blue-green.
It just looks like the green of these fields. But if you come in the oxidized zone, it's much more yellow, and not the green. And that's because of the relative amount of ferrous and ferric in the things. And again, that's a very abrupt change as you go from the oxidized zone to the unoxidized zone.
I'd like to draw your attention to pages 62 and 63 in your guidebook. If you have one, you can take a look at. These are data that were generated by Terry Valadares during his work. And these are data from a handful of profiles that were formed in both the Aquia and the Nanjamoy formations, these glauconitic materials, and they're showing changes in properties as you cross from the oxidized into the unoxidized zones. There's 3 graphs on those 2 pages. The first one is a graph of pH. And 0 on each of these graphs is the boundary between the oxidized and the unoxidized zone. So very close to the boundary, the pH generally runs about 4 to 5.5, and it increases as you go up. It's more sort of a gradual change as you go up. The second graph on the top of page 63 demonstrates the quantity of chromium reducible sulfur. And in many of these, if you come just a few centimeters above the boundary, it's a very sharp morphological boundary. And if you come just a few centimeters above the boundary, the quantity of chromium reducible sulfides drops dramatically. In some cases, it's essentially 0. And then it increases very dramatically to between 0.5 and 1% sulfur as chromium reducible sulfur. And then the last graph demonstrates that essentially all of these materials are hypersulfidic, that they may start out at pHs between 5 and 7, but when we do the moist incubations, they all essentially drop well below 4, many of them down to 3 or below. So these are significant issues, not if you're just sort of farming the surfaces, but if you're doing work that actually doing excavations through highway construction. I don't know what's going on here. Highway construction or other earth-moving housing developments. If you expose this stuff, then it's a very serious environmental issue.
And can you say just a word, Marty, about the water? Anyway, there is quite concern about the groundwater in our state, and one of the things that here at the tobacco farm, they used to be on groundwater.
You don't.
But they're usually a density change across that boundary also. The oxidation loosens the material, so very commonly there is perched water sitting on the top of the unoxidized zone. And this, of course, if you put in a well, just a shallow well, that's what you pump up. And here at the farm, I think I've already spouted off about this before, but anyway, the sinks are usually, they used to be just a nice reddish brown color from anyway, there's a lot of iron in that water coming out. But also concerned about other things, because of course there's arsenic associated with sulfide minerals and other kinds of things. So it is a groundwater issue, and so this thing came up yesterday about how deep, what do we have to call, post-active acid sulfate soil, early post-active, middle-aged soil, that kind of thing. But it's still very significant that those sulfides are down there, to the water, to the land disturbance, to all those kind of things. And all of that we largely miss if we stop at 2 meters. Although sometimes we do find in New Jersey and other places, I know Gary could support me on this. I was up and saw some soils in New Jersey where actually the boundary to the unoxidized zone is above 2 meters. There are places in New Jersey where